Welcome to lecture 33, linear equations with constant coefficients. Linear differential equations, constant coefficients. So we're now going to talk about higher order, potentially linear equations, but they all have constant coefficients. So we have the nth derivative of y plus p1 times the n minus first derivative of y plus p2 times the n minus second derivative of y, and so forth all the way up to pn times y is equal to f. But here, the pi's are numbers, not functions. And because of that, we're going to simplify our notation a little bit by using the differential d equals d by dt, and think of this as a polynomial in capital D acting on y, and then we get d to the n plus p1 d to the n minus 1 plus p2 d to the n minus 2, all the way up to plus pn minus 1d plus pn acting on y is equal to f. And the homogeneous equation, of course, is the situation where f is replaced by 0. So this is the equation we have to solve. And this is just a recap of what what we're going to call this polynomial. We're going to call it p of capital D. It's just that expansion in the parenthesis above, d to the n plus p1, d to the n minus 1, and so forth all the way out to pn. And then the homogeneous equation is symbolically p of capital D acting on y is equal to 0. And now what we do is we factorize that polynomial. There'll be m roots ri such that p of d is equal to d minus r1 raised to the k1 power, d minus r2 to the k2 power, all the way out to d minus rm to the km power, where ki does not necessarily have to equal 1. I could have multiple roots. But the sum of all of the k's, that's got to equal n because that was the order of the polynomial. It was an nth degree polynomial. Okay, the roots can be complex even if all of the coefficients are real. We know that even from quadratic equations. But because the coefficients are all real, that means the polynomial is equal to its complex conjugate. That means any roots that are complex must come in complex conjugate pairs. So if there's an ri that is complex, then there must be an rj that is equal to ri star. And of course, I must have the same multiplicity of those roots, so ki must equal kj in that case. And we're going to concentrate on the solution of the homogeneous equation. We're going to, at the end, give one example of how to solve an inhomogeneous equation. And that's simply because we already have this technique that's a cookbook that works for solving the inhomogeneous equation called the method of variation of parameters. It's unfortunately a really painful and unpleasant method, but it does work if you can manage to push your way through all of the algebra and get all the way to the end. All right, so how do we solve these homogeneous equations? We want to find n solutions because it's a order n differential equation. And by using the factorization, we're going to look at each term in the factorization one after another. And so we're going to have a term that looks like d minus ri raised to the ki acting on y is equal to 0. And so how do we find a solution to this? Well, we're going to do what is effectively an integrating factor. But I first want to note that if I find a solution to that equation, it will also solve p of d acting on y equals 0 because the different derivative factors all commute with each other. And that's because the r's are all numbers. None of those are functions of t, and so the derivative goes right through them, and the derivative, of course, commutes with the derivative itself, and so because of that, everything works out perfectly fine, and we can tear apart the large polynomial in terms of its factors and just solve the equation for each of the factors and then put it all together. So we're going to start with ki equals 1. This is actually a pretty easy equation to solve. It's our first order linear differential equation with constant coefficients. We had an explicit formula for how to solve it, but we're going to write it down in terms of an integrating factor in the following way. We're going to write d minus ri acting on y equals e to the rit times d e to the minus rit acting on y. And let's just prove that right now. So it's going to be e to the rit d e to the minus rit acting on y. If I take that derivative, I'm going to get the derivative acting on the first term, which is going to give me minus ri e to the minus rit times y, plus e to the minus rit times the derivative acting on y. Now when I multiply by e to the RIT on the left, those exponential factors cancel. I just get minus RI plus D acting on y, and then of course I just change the order inside the parenthesis. I get D minus RI acting on y, which is what we claimed it was equal to. So we've now proved that identity. And what do we do with that identity? Well, if we have the equation d minus ri to the ki acting on y, we're going to use that identity one after another after another after another until we've exhausted it to the end. So we already know we can replace one of the factors d minus ri acting on y by e to the rit d e to the minus rit acting on y. But now I can think of that object to the right of those ki minus 1 derivatives as being some new function y bar. And then I can just use this identity acting on the y bar. And when I do that, when I multiply by e to the minus rit, that'll cancel the exponential factor. I'll take the derivative, that'll make the derivative into a square of the derivative, and then I have to multiply by the e to the rit on the left. And you see it maintains that same form. I just get the derivatives raised to a higher power. So you immediately can see when I iterate this ki times, in the end I get e to the rit d to the ki acting on e to the minus rit times y, and that is what that equation is. It's a different way of writing the equation in terms of what is effectively an integrating factor. Okay, so we want to solve the homogeneous equation. So we set that equal to 0. And that means we can cancel the e to the rit on the left-hand side. We just multiply by e to the minus rit. And that means I have the kth derivative of the thing inside the parenthesis is equal to 0. Well, if the kth derivative of something is equal to 0, then it's simply a polynomial of degree ki minus 1. Because if I take k derivatives of that, every term in that polynomial is going to give 0. So we immediately learn e to the minus rit times y is equal to c0 plus c1t all the way up to ck I minus 1 t to the ki minus 1. We multiply by e to the rit and we get our ki solutions. It's the exponential times t, the exponential times t squared, all the way out to the exponential times t to the ki minus 1. And those will be ki independent solutions of the homogeneous equation. So we've now solved or found the solutions for one of those factors. Effectively, it's just the exponential of the root times t, and then I add powers of t up to ki minus 1. So I start with no powers of t, and I go all the way up to ki minus 1, and then I stop. And those are the independent solutions to that simple differential equation. Now, to solve the whole equation, we now do this for the other factors, very easy to write down, and then we get all of the solutions to the polynomial acting on y is equal to 0. All right, so the full solution is then a linear combination of all of those different solutions that we found. So if I look at the first root, it'll be e to the rit, te to the rit, all the way out to t to the k1 minus 1 e to the r1t, and similarly for r2, and all the way out to rm. The ki's do not need to be the same. They can change for each root. And if we take this object and we calculate its Wronski and take the determinant of that, we will find the determinant is non-zero. So all these solutions are indeed independent of each other. Okay, the general solution of the homogeneous equation is then a linear combination of all of these solutions. And then if I want the solution of the inhomogeneous equation, I have to add a particular solution of the inhomogeneous equation. Now, when I have real roots, I just use these exponential factors. If I have complex roots, it's often better to take linear combinations of those complex exponentials and rewrite them in terms of real functions. So we're going to replace e to the I bit, e to the minus I bit by cosine bit and sine bit, because I can do that in terms of different linear combinations. So we find one of these solutions will be t raised to some power, that power could be 0, times e to the ait times cosine bit, and t to the alpha e to the ait times sine bit. And all of those functions are real now because the ai's and the bi's are real objects. And so you have to just remember when the roots are complex, we're going to be using cosines and sines of the imaginary part of the complex numbers instead of just plain exponentials. Of course, they simply are related by a linear combination, but it turns out in doing calculations, it's much easier to work with the cosines and with the sines. So, as with anything, when you have something complicated like this, you hear about it, it kind of goes over your head rather quickly. We got to take a look at some concrete examples. So let's start taking a look at some examples. Our first example is to solve the following equation. D to the fourth minus 4d cubed plus 4d squared y equals 0. Now, we have the polynomial p of d is d to the fourth minus 4d cubed plus 4d squared. We have to factorize that, and you very quickly can recognize that factorizes into d squared times d minus 2 quantity squared. So the four functions that are going to solve the homogeneous equation, for the d squared, I will get 1 and t, because the exponential of 0 times t is just a constant. And for the d minus 2 squared, I'll get e to the 2t and t e to the 2t. And then those are the four linearly independent solutions to the homogeneous equation. So let's check that they are independent. So we're going to form the Wronskian, and then we're going to take the determinant. And so in the first line, we write the function. In the second line, we write the first derivative. In the third line, we write the second derivative. And in the fourth line, we write the third derivative. And all of those derivatives are really easy for the first three functions. I have to work a little bit to get the derivatives right for the third function, but if you keep your wits about you, it's really not that difficult to work those out. And so you see here, it's almost in upper triangular form. I only have that one term in the lower triangle, the 8e to the 2t, that I got to get rid of. So I'm going to multiply 2 times the third row and subtract that from the fourth row. So when I multiply 2 times the third row and subtract from the fourth row, I then have a upper triangular matrix, and all I have to do is take the product of the diagonal elements to get the determinant of the Wronskian. And if I do that, I'll get 1 times 4e to the 2t times 4e to the 2t, and so that's equal to 16e to the 4t. And of course, that's never equal to 0, so that shows that the functions are indeed independent. All right, let's take a look at our next example. We're going to solve the following equation: d to the fifth plus d to the fourth minus d cubed minus 3d squared plus 2 acting on y is equal to 0. So we have our polynomial p of d. It's this quintic polynomial, and we got to find the factors of this. And in general, you know, this is not so easy to factorize, but there's this wonderful theorem that you probably never learned in high school, but you wish you had learned it. It's certainly one that you should remember if you can. The real roots of a polynomial with integer coefficients are given by a ratio p over q, which is written in lowest terms. So p does not divide q, they have no common factors. And the factor p divides the constant term, which is here 2. And the factor q divides the highest power term, the coefficient, which is here 1. The coefficient of d to the fifth is 1. So q can be plus or minus 1, and p can be plus or minus 1 or plus or minus 2. And when I look at the ratio of p to q, I get plus or minus 2 or plus or minus 1. So we now just plug these into the equation and see if they work. So let's try 1. I would get 1 plus 1 minus 1 minus 3 plus 2. Well, that's equal to 1 plus 1 is 2, minus 1 is 1, minus 3 is minus 2, plus 2 is plus 2. So that works. Let's try minus 1. I would get minus 1 plus 1. That gives me 0. I would get plus 1 minus 3, that gives me minus 2, plus 2, that's equal to 0. So we immediately find that 1 and minus 1 are roots. So d plus 1 times d minus 1 is equal to d squared minus 1. And so I can factorize p of d in terms of those two factors I just determined, d minus 1, d plus 1, times a cubic, d cubed plus d squared minus 2. Well, once again, I don't exactly know how to factorize this cubic, but let's see if it has any simple factors. Once again, p can be plus or minus 2 plus or minus 1, and p can be equal to, q can be equal to plus or minus 1. And so we will try 1 in this equation. If I try 1 in this equation, you immediately see it's 1 plus 1 minus 2. That's equal to 0. So there's an extra factor of 1, so I get a d minus 1 squared, and then I get a quadratic that is left after I divide d cubed plus d squared minus 2 by d minus 1, I find it's equal to d squared plus 2d plus 2. And now I use the quadratic equation to find the roots of that. Using the quadratic equation, we get minus 1 plus or minus the square root of 1 minus 2. Well, 1 minus 2 is minus 1, so that becomes minus 1 plus or minus I. And so now we know how to form our solution. We have all of the 5 roots. 2 of them are equal to 1, 1 is equal to minus 1, and 1 is equal to minus 1 plus or minus I. And so following the rules that we have, we're going to take the following solutions. We're going to look at e to the t times e to the t, e to the minus t, e to the minus t times cosine t, and e to the minus t times sine t. All right, and the linear combinations of those are going to solve the homogeneous equation. All right, let's look at our next example. We want to solve the following equation. D to the 4th minus 16 acting on y is equal to cosine t. Now, d to the 4th minus 16, I can immediately factorize that. It's d squared minus 4 times d squared plus 4, which is d minus 2 times d plus 2 times d minus 2i times d plus 2i. And now I can form my homogeneous solutions. There are 4 of them. It's going to be e to the 2t, e to the minus 2t, it's going to be cosine 2t, and it's going to be sine 2t. And those are the 4 independent solutions that we're going to be using for the homogeneous equation. To solve the inhomogeneous equation, we've got to find a particular solution. And so I'm going to show you how we do variation of parameters. It's really a bit of a mess. It's going to take a couple of slides. But I really want to press upon you that if you just are careful and carefully work this stuff out, you can get all of these things to work. And so the first thing we have to do is we have to form this Wronskian matrix. So we take e to the 2t, e to the minus 2t, cosine 2t, sine 2t, and then we take the derivative, and then the second derivative, and then the third derivative, are each of those rows. And those things multiply a1 dot, a2 dot, a3 dot, a4 dot, and they're going to equal 0, 0, 0 cosine t. Okay? And so the way we're going to solve this equation is by row reduction. It's a little bit of a mess, so we're going to have to go carefully through it. But if we look at the first situation, I'm going to take 2 times the first row, and I'm going to subtract it from the second row, and I'm going to take 4 times the first row and subtract it from the third row, and I'm going to take 8 times the first row and subtract it from the third row. When I do that, I'm going to get zeros in that first column below the diagonal. Okay, so this is now just repeating what I had said we're going to be doing, and now we're going to see what does it give. So I get those zeros, and then I get a minus 4 e to the minus 2t. I get another 0, so I don't have to worry about that term, and so forth. So now what I have to do is I have to take 4 times the second row and subtract it from the fourth row, and that'll give me another one of the zeros. So let's go ahead and do that. The first row, the second row, and the third row all remain unchanged, and with the fourth row, when I do that subtraction, I'm going to get a simplification in the end. I'm going to get just a minus 8 cosine, a 16 sine 2t, minus 16 cos 2t, and of course I just have cosine t because it's zeros for all the terms above it. Now I got one last thing I got to do. I've got to take the third row, multiply it by 2 times the tangent of 2t, and add it to the fourth. Okay, so we take the third times 2 tangent 2t and add it to the fourth. And now I got all of my zeros. I've got my lower triangular matrix, and I've got the diagonal in the upper triangular part. And I'm trying to now take the 4 by 4 matrix, which is the left-hand part of this matrix, multiply it by the AI dots, and I've got to equal this object, which is the last column. All right, so we now have to do back substitution or back solving to get the AI dots. Okay, so here's where we are. Now, to do the back solve, we'll start with the fourth equation. The fourth equation just says minus 16 secant 2t equals cosine t. So that gives me a4 dot equals minus 1 over 16 cosine t cosine 2t. Now I plug that into the third equation, and I find a3 dot is going to equal minus sine t over cosine 2t times A4 dot. I already know what A4 dot is, so I'm going to get 1/16 cosine t sine 2t, and that's A3 dot. And now I have to plug into the second row to get A2 dot. A2 dot is going to equal e to the 2t times minus 1/2 cosine 2t plus sine 2t A3 dot plus 1/2 cosine 2t minus sine 2t A4 dot. Now I got to substitute in what A3 dot and A4 dot are, and I have to go through some algebra, but it actually simplifies rather nicely. When all the dust settles, I find it's equal to minus 1/32 e to the 2t times cosine t. And now I got to go to the first row. I got to substitute in for the A2 dot, the A3 dot, the A4 dot, so that I can get the A1 dot. And so my equation for A1 dot is minus e to the minus 2t times e to the minus 2t A2 dot plus cosine 2t A3 dot plus sine 2t A4 dot. I plug in those solutions I already have for those AI dots. I then simplify to the best of my abilities. You can see that the second and third terms are exactly equal, and so they cancel because they have an opposite sign. And I'm left with 1/32 e to the minus 2t times cosine t. Okay, so we've now gotten all of the AI dots. We're not done yet. We still have to integrate those to get the final results. So here are the equations that we have. That's A1 dot, A2 dot, A3 dot, and A4 dot. So now some of these are pretty easy to integrate. Others are kind of tortuous. So for example, A3 dot is not too hard to integrate because I can replace sine 2t by 2 cosine t sine t, and you see sine t is the derivative of cosine t, so that would be the integral of cosine squared t sine t, which would just equal cosine cubed t over 3. Okay, now the other ones get a little bit more complicated, and we have kind of gone over how you solve these kinds of equations, how you integrate them, but the reality is this is now a time where you use something quickly. So let's go ahead and look up in a table, or let's go ahead and use Wolfram Alpha or a similar device to actually evaluate these integrals, and then we're going to get our final answer. So I want you to make sure, particularly on things like homework, it is perfectly fine to use integral tables or Wolfram Alpha at this stage to get the different results. And also remember, we're looking for antiderivatives here. We don't have to worry about the constants because the constants don't enter into the results that we're trying to work out for this equation. So now when we go ahead and solve those integrals, you really get these complicated beasts. A1 of t is minus 1/32, the real part of e to the minus 2 plus I times t divided by 2 minus I, and so forth. I mean, all these equations are kind of complicated. I haven't even written A4 yet. A4 is not so bad. And so we now have to take these objects, multiply them by the corresponding y of t's, and add them all up in order to get the particular solution. Okay? So I have to take A1 of t times y1 of t plus A2 of t times y2 of t plus A3 of t times y3 of t, and so forth. And now it's still quite a mess. I have to work on simplifying this some more. And so there's a fair amount of algebra that goes in. But when the dust all settles, you find it's equal to minus 1/15 times cosine t. Okay, so the end result is actually pretty simple. It's just horribly painful getting through this. Now we can immediately check that if I take the fourth derivative of minus 1/15 cosine t, I'm going to get minus 1/15 cosine t. And if I add 16 of those, subtract 16 of those, I'm going to get minus 1/15 cosine t plus 16/15 cosine t, and so that becomes 15/15 cosine t, or it just equals cosine t, which is indeed what this particular solution has to equal. So it does work, but it is a rather long calculation and not one that is all that pleasant to have to go through. We're going to show you in the next lecture an easier way to solve these problems if you can make good guesses as to what general form the particular solution must be.